subject measurement and instrumentation. So this subject comes for second year fourth semester. Comes in the second year fourth semester. So today's topic is about classification of instruments. So we can classify the measuring instruments into two categories. One is absolute instruments and the second one is the secondary instruments. So absolute instruments give the measurement quantity of the instrument in terms of constant and deflection. And the secondary instrument gives the deflection of the electrical quantity to be measured directly. So the classification of secondary instruments. So again, the classification of secondary instruments can be classified into indicating instruments, recording instruments, and integrating instruments. So the indicating instruments means, so the instrument which uses pointers and dials, we call this as indicating instruments. The instruments which records the quantity of measuring, we call this as recording instruments. Then the instruments which measures the total quantity of electricity delivered to the consumer, we call this as integrating instruments. So we can use this the instruments based on we can use these instruments for ammeter and voltmeter. So we can categorize this ammeter into moving coil type meters. We can use this moving coil meters for both the DC and the AC, and the moving iron type meters for both the DC and the AC. Induction type. So again, induction type we can categorize into split type and shaded pole type. So the first one for measurement of DC, here we use permanent magnet, the moving coil instruments by the name PMMC instruments. So here in the permanent magnet moving coil instruments, why we call this permanent magnet moving coil? Magnet is permanent, hence the coil is moving, hence we call this instrument as permanent magnet moving coil. You can see here, you can see from this, so the magnet is the permanent which produces a radial field, but the moving coil which is we are suspending the moving coil in the radial field. You can see from the figure, in the radial field the moving coil is suspended. So the unknown current which is measured is given to the moving coil, and the current carrying conductor is placed in the magnetic field. It experiences the force. Due to force, the pointer shows the corresponding values of the current or the voltage. This is the working principle of the PMMC instrument. You can see the shapes of the moving coil. You can categorize the shapes of the two moving coils into two shapes. One is the circular shape, the second one is a rectangular shape. You can see that in the diagram, the rectangular shape of the moving coil has been shown. This rectangular shape has been suspended in the radial magnetic field. Over the moving coil, you can see that the aluminum former is covered. The moving coil is covered with the aluminum former to provide necessary dampings. The torque equation of the PMMC. So as we know that what the deflecting torque. So PMMC instrument uses magnetic effect to obtain the deflecting torque. So you can see the torque equation of PMMC instrument is deflecting torque equal to NBAI. N stands for number of turns of the moving coil, and B for flux density in Webers per meter square. A is the effective area of the coil in meter square. I is the current to the moving coil in amperes. Then to obtain the control torque. So as we know that what the control torque which opposes the cost produced by the deflecting torque. So TC equal to K theta. So here K is a constant or spring constant, theta is the deflection, TC is the control torque. At a steady state condition, when TD is equal to TC, So TD we know that LBAA, TC equal to K theta. When we substitute this at the steady state condition, theta equal to K divided by G into I. So from this equation it's very clear that the current is directly proportional to deflection. This is the second method, moving ion attraction type. So in this moving ion attraction type, you can see the name itself it implies that based on attraction of the iron bar, the pointer shows the values of the current or voltages. You can see it's very clear. This moving ion instrument system uses damping, air friction damping used for damping methods, and to get the controlling torque, the magnetic effect is used, and for spring control it uses gravity control method is used. Okay. You can see here from this the two fixed coils. The fixed coils are just like a hollow opening. You can see from this the fixed coils are there. Okay. Just like what a hollow slot opening, the two fixed coils, and the current to be measured is mounted on this fixed coils, and the spindle, over the spindle iron bar is there. So when this iron bar is brought very nearer to the fixed coils, iron bar get attracted by the field coils. So due to attraction force, the pointer shows the corresponding values of the current or the voltages. Okay. So this is another method, the moving ion repulsion type instruments. So in this moving ion repulsion type instruments, it uses fixed coils followed by why it is called moving ion repulsion type instrument means the working principle based on repulsion of the magnets. Okay, here you can see from this diagram you can observe that the like poles are repulsed each other. Okay, so here how the like poles means the vanes which are arranged for repulsion type instruments. There are two vanes are there. One of the vein is attached to the fixed coils, another vein is attached to the spindle. Okay. Unknown current which is to be measured is given to the fixed coils. This due to the current, the fixed coil gets energized and produces the magnetic field. This magnetic field makes the repulsion force on the vanes. This makes the vanes to move from its places. Due to what repulsion force, the unknown values of the current is measured using the pointer. So name of this method is radial vane type. So in the moving and repulsion type instrument, name of this method is radial vane type. Why we call this radial vane type means the shape of the vanes are radial. Next, this is another method of moving ion repulsion type. Here we use coaxial vane type. Why we call this coaxial vane type means in the vanes are in the coaxial shape. We call this as a coaxial vane type. So here also consists two vanes. The one is attached to the fixed coils. Another vane is attached to the spindle. So again the unknown values of current is given to the fixed coils. The fixed coils get energized, which makes the repulsive force on the vanes. So due to repulsive force, the moving vane move from its original place. The corresponding pointer will shows the values of the current or voltage. So you can see here the deflecting torque is proportional to the square of the current. You can see from the equation it's very clear. The deflecting torque TD is equal to 1 by 2 of I square into dl by d theta. dl for change in inductance, d theta for change in deflection. Then we can controlling torque. So we can get controlling torque is Tc equal to k theta. So the controlling torque is directly proportional to theta of the deflection. So at the steady state condition, TD is equal to Tc. So theta equal to 1 by 2 I square divided by k into dl by d theta. So with this, this session is completed. So moving ion attraction type and the moving ion repulsion type are completed for measurement of current or voltage.
Cool.